Okay. So, hi everyone. So, good morning here. Good morning to everyone. Okay. Good morning all. Okay. So, okay. So, in the live chat, so they have shared a link here. They have shared a link to fill the Google form. So, please go through that and fill that Google form here. Okay. 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 So, yesterday's class here. In yesterday's, that means in previous session, we have seen the concept of average value and RMS value. So why we have to calculate average value and why we have to calculate RMS value. So all these things we have seen here in the previous session. Okay. So we have seen what is the purpose of this average value and what is the purpose of this RMS value and all these things. Okay. So that's what we have completed in the previous session. So today I'm just revising the previous session here, and then after that we will see the piecewise linear model of diode, and also we are going to study about the rectifiers and all those things. Okay. So before that, I'm just revising what we have done yesterday. See here. So we have determined average value and also we have determined RMS value. We have seen how to determine average and RMS value and the purpose of them also. Okay. So how to calculate average value here? If suppose if you are having some function x of t, so how to calculate average value? Okay, you have to integrate this throughout its time period and you have to divide with its total time period. So this is nothing but average value here. This is how you have to determine the average value for this function, that is x of t. So how to determine RMS value here? So I have explained here, I have explained clearly the reasoning behind this. What is the purpose of this average value, RMS value, all these things I have explained in the previous session. Okay. So RMS value is nothing but what here? 1 by t integral 0 to t x square of t dt under root. So these are the mathematical expressions that we have derived, for average value and RMS value. Right. Okay. Okay. Yeah. Now if suppose if you are having a signal here, v of t, let us say you are having a signal v of t, right? Okay. So that signal may have what here? That signal may have both DC component as well as what? AC component. In general, it may have both DC component and AC component. So in the previous session, I have told that whenever you are calculating the average value of a signal here, the average value of a time varying signal. Okay. So it is going to give you what? It is going to give you some constant value that is going to represent the DC component of the signal. So whenever you are calculating average value of a signal, it is going to give you the DC component that is present in that signal. So in general here, if you consider any signal, it may be a combination of what? It may be a combination of both DC as well as what? As well as AC, right? Okay. So now let us consider that type of signal here, which is having both DC as well as AC. So let us say V of t. So V of t is having, let us say it is having DC as well as what? As well as AC. So DC is pure DC here, AC is pure AC, right? Okay. So it is a combination of both DC and AC. I have explained also what do you mean by pure DC signal and what do you mean by pure AC signal in the previous session. Okay. So this is lecture 4 on analog circuits here. So I have taken in lecture 3. In lecture 3 you can refer and you can revise what do you mean by pure DC, what do you mean by pure AC, what is average, what is RMS, all these things I have explained there. Okay. Okay. So V of t is equal to, it may have both DC component as well as what? As well as AC component. Now for this type of signal, how to determine RMS value? How to determine RMS value? Tell me. So RMS value of this signal is equal to what? Is equal to square root of 1 by t integral 0 to t, and you have to square this signal. Yes or no? We are trying to determine the RMS value of this signal, right? Okay. So you have to square this signal, that is v square of t into dt, Yes or no? Okay. See, 1 by t into integral 0 to t v of t dt is nothing but average value of voltage signal. Average value of voltage signal. Yes or no? Or you can say mean value of voltage signal. So if you square this here, if you square this, you can say mean square value. You can say mean square value. And if you put root, you can say root mean square value. Root mean square value. Okay. Okay. Yeah. Okay, so now see here, so this is equal to what? Yeah, this is equal to, so this is equal to square root of 1 by t integral 0 to t. This v of t is having what? Yeah, both DC component as well as what? AC component. DC component as well as AC component. So substitute in place of v of t this vdc plus vac here. So what you are going to get? vdc plus what? Plus vac whole square dt, right? Yes or no? Okay, so now expand this. So this is vrms here, vrms. So vrms is equal to what? vrms is equal to, so square root of what you are going to get here? 1 by t integral 0 to t. So expand this here, what you are going to get? You are going to get vdc square plus vac square plus what? 2 into vdc into vac. Yes or no? So this is what you are going to get. So now if you integrate this, what you are going to get? So square root of 1 by t integral 0 to t vdc square dt plus 1 by t integral 0 to t vac square dt plus 1 by t integral 0 to t 2 vdc into vac into dt. Yes or no? Okay, so this is what we got here. See, from here if you observe, this one here, if you observe this term, okay, so here this is DC here, this is pure DC. DC means it is constant with respect to time, so you can take it out of the integration, right? So if you take it out of the integration, you are going to get 2 vdc by t integral 0 to t vac dt. So vac represents what here? Pure AC signal, So for any pure AC signal here, what is its average value here? Average value of any pure AC signal is always equal to what? Is always equal to 0. Yes or no? Okay, so the average value of pure AC signal is always equal to what? Is always equal to 0, right? Okay. Why here? Because in pure AC signal there will be no DC component. So DC component is equal to 0 means average value will become equal to 0. See, what is this? This is nothing but, if you take this 2 VDC separately, okay, you are having what? 1 by T integral 0 to T VAC dt. So this one 1 by T integral 0 to T VAC dt will represent what? Will represent the average value of pure AC signal. So this will go to what? This term will go to 0. This will go to 0. So that means this total term will go to what? Will go to 0. Will go to 0. Right? Okay. Next, see here. So what you are having? So here this is VDC here, VDC. So VDC square means it is constant with respect to time. So you can take it out of the integration. So you are going to get VDC square by T integral 0 to T dt here. Integral dt is nothing but T, and if you substitute the range, you are going to get here T. Right? Okay. So plus what is left out here? What is left out? So 1 by T integral 0 to T VAC square dt. Right? Okay. So now here T will get cancelled. So you can write it as square root of what? Square root of VDC square plus. So what is this one here? What is this one? 1 by T integral 0 to T VAC square dt. So I can represent this as what? I can represent this as VAC RMS square or not? Yes or no? Yeah, VAC RMS square. Yes or no? Okay. See this how it is looking like. It is looking like a mean square value or not? mean square value, that means RMS square value. Yes or no here? Yes or no? Okay. Right. So this is RMS value. So if you square this, what you are going to get? 1 by t integral 0 to t x square of t dt. So here also the same thing or not? Okay. So this total term, you can write it as what? VAC square RMS, VAC square RMS. Right. Okay. So you can write it as VAC square RMS. VAC RMS square. Right. Okay. So this is nothing but VRMS here. VRMS. So now if you square on both sides here, what you are going to get? VRMS square is equal to what? Is equal to VDC square plus what? Plus VAC RMS square. So this relation is very, very important here. This relation is very, very important in case of what? In case of rectifier circuits. Okay, so the total signal, for the total signal we can calculate the RMS value. Total signal may consist of what? Both AC component as well as DC component. So if you try to determine the RMS value of that of the total signal, you can represent it as what? VRMS square is equal to what? VDC square plus what? VAC RMS square. Right. Okay. So now here if you particularly want RMS value of this AC signal here, so this is equal to what here? This is equal to square root of what? Square root of VRMS square minus what? Minus VDC square. So in this manner you can determine for a pure AC signal, you can determine the RMS value. Right. Okay. So or I can say in a signal for AC component, you can determine the RMS value in this manner. So that is square root of what? Square root of VRMS square minus what? Minus VDC square. Okay. So now here we can analyze this DC component and AC component here. That means whenever we are analyzing rectifier circuits, there we can compare the DC component with respect to what? With respect to AC component, or AC component with respect to DC component. If we want to compare DC component with respect to AC component and AC component with respect to DC component, that we can do from these equations here. Yes or no here? Okay. See, if you want to compare VAC RMS, and that means AC signal and DC signal, so then you can write VAC RMS by VDC. So this is going to give you what? This is going to give you the comparison between what? VAC RMS and VDC. Or you can compare the total DC voltage, with respect to what? With respect to the total voltage of the signal, that is the total RMS value of the signal. So in this total signal, how much of the component is DC? Okay, in this total signal, how much of the component is present as DC? Right. So in this manner you can compare. Right. Okay. So here you are comparing AC with respect to what? With respect to DC. AC with respect to DC. Here you are comparing the DC component with respect to what? With respect to the total signal. That means within the total signal, what fraction of DC component is present? That is given by this ratio. Right. Okay. So we know that here VAC RMS. Okay, so VAC RMS is nothing but what? Is nothing but RMS value of pure AC signal, and this is nothing but DC signal. This is nothing but DC voltage. So always AC signal is going to ride over. Yes or no? This AC signal is going to ride over this DC signal. Yes or no? So if you are having DC, so this AC component is going to ride over this DC component, Okay. Now if you want to compare this AC component with respect to this DC component, then you have to take this ratio. Okay. So we are going to see all these things in rectifier circuits here. Okay. So I hope these expressions are clear here. Okay. Is it clear here? Is it clear up till now? Yes or no here? Yes or no? Is it clear? Yes? Okay, yeah. So I hope it is clear here. Up till now, I hope it is clear. Okay? Okay, yeah. So next. So I said this ratio will give you what here? How much AC component is riding over the DC component. How much AC component is riding over the DC component. So this ratio is going to give that. Okay. And this ratio is going to give you how much factor of DC component is present in the total signal. So this ratio is going to give you this one here. So actually this ratio we call it as ripple factor. We are going to see that here, no problem. Okay. And here we are comparing the DC component with the total signal here. Okay, we will see all these things here. We will see all these things, no problem. Okay, next here. So now you are clear with average value, RMS value, and the relation between RMS and DC and AC RMS, all these things. Yes or no? Okay. Okay. So now, we'll move on to diodes here. Okay. So now here I am going to explain you how to analyze the diode circuits. Whenever you are having a diodes in a circuit, how to analyze that circuit. Diode is a non-linear element or not? Yes or no? So dealing with non-linear elements is not that much simple as you are dealing with linear elements here. Yes or no? Okay. So how we are going to handle, and how we are going to analyze the circuits that are having what? That are having non-linear elements like diode. Okay. So that's what we are going to see now. Now here we know that the current versus voltage characteristic of a diode. Yes or no? Okay. So we know the voltage current versus voltage characteristic of a diode here. So I am drawing the characteristic. I am drawing the VI characteristic of a diode. So here, so let us consider a diode here. Let us consider a diode. Okay. So this is P side and this is N, or you can say anode and cathode. Right. Okay. So now always the current will flow from where to where here? From P to N. Always the current will flow from P to N. Right. Okay. So across this, the potential I am representing as VD, and the current will always flow through the diode always from P to N. So it is not going to allow the current in both the directions here. It is going to allow the current only from P to N. Yes or no? Okay. So in another direction the current will be almost equal to 0. Right. Okay. So it is a unidirectional device. Right. Okay. Okay. Yeah. So now here I am drawing the characteristic here. See here. So wait. So here this is ID versus what? Versus VD. ID versus VD. So how the characteristic will look like here? See here. So okay. Okay. So this is how the characteristic of the diode will looks like. That is I versus V characteristic. Right. Okay. Okay. Yeah. Now see here. See, so here in this region from here to here, so whenever the diode is operating in this region here, whenever the diode is operating in this region, we call this as reverse bias region. We call this as what? Reverse bias region. Okay, reverse bias operating region, reverse bias operating region, right? Okay, so let us consider from here to here, let us consider from here to here. So this is nothing but forward bias region here. This is nothing but forward bias region. But here, what is the current that is flowing? The current is almost 0 here. So this is forward bias region, but negligible current here, negligible current. Okay, current is approximately, you can consider as 0. Okay, next, a significant amount of current will flow once it reaches a cut-in voltage. Okay, it reaches cut-in voltage. So let us say this is V gamma. Let us say this is V gamma. Okay, so this is nothing but cut-in voltage here. This is nothing but cut-in voltage. So once the voltage drop VD across the diode crosses this cut-in voltage, then only the significant amount of current will flow through the diode, So below this cut-in voltage, even if the diode is operating in forward bias region, it is going to have negligible amount of current, that is almost equal to 0. And whenever it is operating in reverse bias region, here also the current is what here? The current is almost negligible. The current is almost negligible. So here in this region and in this region, the current is almost negligible. So here once you cross this cut-in voltage, the current is having some significant value. And here see how we are getting these characteristics and all these things that you are going to study in your EDC here. Here we are going to utilize these characteristics in order to analyze the circuits here. Right, okay. So here this voltage we call it as what here? We call it as breakdown voltage. Okay, breakdown voltage. So we are not going to operate the diode in this region. So this is breakdown region here. This is called as what? This is nothing but breakdown region. So a normal diode you should not operate in this breakdown region. Okay, so there are some diodes which are specifically designed in order to operate only in breakdown region, that is called as Zener diodes. I am talking about normal diodes here. Okay, so if you consider simple normal diodes, so you cannot operate those diodes in breakdown region. So this breakdown region is nothing but what? Is nothing but non-operating region. This is nothing but what here? Non-operating region. Right. Okay. Now similarly, see here. You can take any electronic device here. You can take any device. Okay. So here VD into ID. So if you multiply VD into ID here, VD into ID will give you what? Will give you the power that is dissipated across the diode, right? The power that is dissipated across the diode. So whenever you are applying some voltage across a device and some current is flowing through that device, then V multiplied by I is going to give you the power that is dissipated across that device, right? Okay, so for any device here, for any device or for any component, so for each and every component it is going to have its own power handling capability. Yes or no? It is going to have its own power handling capability. So that means that device can sustain only up to some power here. So if the power across the device goes beyond that value, then it cannot handle that much of power, or it cannot handle that much of heat that is generated. Yes or no? And heat that is generated across the diode here, across the device. Right. Okay. So so what will happen here? If it goes beyond that value here, if it goes beyond that power limit, so what will happen? Heat generated across that component will become more and more and more, and it cannot tolerate that much of heat. And finally, what will happen here? That the device or component may get what? May get burned away. Yes or no? So once it get burned away, what is going to left? Only ash is going to left out. Okay, you have to take that ash and keep it like this. There will be no use. Yes or no? So for any device here, for any device or component, there is a power handling capability or power handling limit here. It is having power handling limit. Okay, so beyond that limit, if the power across the device or component goes beyond that limit, okay, so then the heat generated across the device or component will be more, and that device cannot tolerate that much of heat, and it will get what? It will get burned away. Right. Okay, so always you have to take care of our operating region here. Always you have to take care of the voltage across the device and current across the current that is flowing through the device. Okay, you have to take care of V and I. Okay, across any device here, across any device, such that always it should not go beyond their power limits. It should not go beyond their power limits. Okay, that you have to always take care. Right. Okay. Yes or no here? Okay. Now see here. So in forward bias also here, in forward bias also, you should not go on increase VD here. If you go on increase VD, ID will also goes on increases. But what I said, for any device there is a power handling limit. Yes or no? It cannot go beyond that. You cannot go beyond that power limit here. So let us say the maximum voltage that it can handle across the diode is VD maximum, and here ID maximum. So here this point is nothing but PD maximum. This point is nothing but PD maximum, which is equal to what? Which is equal to VD maximum into what? Into ID maximum. So this is the maximum power that it can tolerate. So you should not go beyond that here. You should not go beyond that. Okay. So now here from here to here, okay. So from here to here. So this is also what? This is also forward bias operating region. But here what is happening here? Significant amount of current will flow. Significant amount of current. Significant amount of current will flow. Okay, so in this region it is operating in forward bias region only, and in this region you are going to see what? Significant amount of current will flow through the diode. Okay, so here it is forward region but negligible current. Here it is reverse bias region and current is almost negligible, and here it is breakdown region, that is non-operating region for a normal diode. And this one here, so if you go beyond this, okay, so this is non-operating region. You should not go beyond this here. So because here the power dissipation across this diode is PD maximum, you should not go beyond that limit. Right. Okay, so I have defined all the operating regions of the diode. Yes or no? Okay. Okay, yeah. Okay. So is it clear here? Is it clear? Yes or no here? Is it clear? Okay. Now see here. So now mathematically, this is graphical analysis I have given here, ID versus VD. So mathematically how these two are related here? Tell me mathematically how these two are related. So we know that ID, that is the diode current, is given by what here? Is equal to I naught, that is some reverse saturation current, I naught into e power VD by eta VT minus 1. So this is the diode current, right? Yes or no here? So this is the relation between the diode current and diode voltage. So ID is equal to what? I naught into e power VD by eta VT minus 1. Okay, so now this is nothing but what? This is nothing but non-linear relation. Yes or no? Non-linear relation between what? Between ID and VD. Non-linear relation between ID and VD. So now in this case, if you are having a circuit, with a diode, then how to analyze that circuit? So now let us consider you are having some V in here. Let us say some V in, right? Okay, and here you are having some resistor. Here there is resistor, and here I have connected a diode. Like this, right? Okay, and the current that is flowing in this circuit is ID, and the voltage drop across the diode is nothing but VD, right? Okay, so now see here. Now if I want to determine this current here, this current ID in the circuit, I want to determine this ID current in the circuit. Okay, now if I follow exactly this non-linear relation here, then by using this non-linear relation, how we can find out ID? That's what we are going to see first. Okay, so that means I am doing exact analysis here. So if we do exact analysis, is it possible to determine ID or not? That's what we are going to see. Okay, so here, so now in this circuit here, what you are going to get? Tell me what you are going to get. So V in, if you apply KVL, what you are going to get? So V in is equal to what? Is equal to the drop across this resistor, that is nothing but VD. So V in is equal to, you will get, sorry, this is VR here, this is VR, right? Voltage across resistor, VR. So VR plus what? VR plus VD. V in is equal to VR plus VD. I want to determine what? ID. So from here, from this expression, I'll try to determine VD value. So how we can determine VD value here from this? Tell me. So what you are going to get? Send this I naught to this side here. So you will get ID by I naught. Okay, then send this -1 to this side, you are going to get +1. Next, here what you are having? E power VD by eta VT. Yes or no? Okay, so from here, what is VD here? You are going to get? VD is equal to eta VT into what? Into ln of ID by I naught plus 1, right? Yes or no here? Okay. It is simple mathematical analysis here. See here, what I have done, I have applied ln on both sides. And I have done the simplification. So then we are going to get what? VD is equal to eta VT into ln of ID by I naught plus 1. So this is the expression for VD. Okay. Now see, I am trying to analyze this circuit by using exact analysis of the diode here, that means exact relation between ID and VD. That's what I am using here to analyze the circuit. Okay, yeah. So V in is equal to VR plus VD. So now this is equal to VR plus what? Plus VD. VD is nothing but what here? VD is nothing but eta VT into ln of ID by I naught plus 1. Now here, what is VR here? VR is nothing but the drop across what? The drop across the resistor, that is ID into R. So substitute that here, in place of VR, just write ID into what? ID into R. So this is nothing but V in. Yes or no here? Okay, so here we got V in is equal to ID into R plus eta VT ln of ID by I naught plus 1. Okay, so now by using this relation here, can you determine ID value easily here? See here, this is nothing but what? This is nothing but some non-linear equation. So from this equation, it is very difficult to determine what? ID value. So you have to use trial and error methods and all those things, okay, in order to determine ID. So which is very difficult process here, which is very lengthy and difficult process, right? So this is what happening whenever you are dealing with what, whenever you are dealing with the circuit that is having only one diode, that is having only one diode. So that means if you do the exact analysis, then it is going to be very tough for us to analyze the circuit. Yes or no? See, this is the situation for single diode here. If you are having a circuit which is having multiple diodes, okay, so then you are going to get many number of nonlinear equations, and in order to solve those nonlinear equations is very difficult task, right? Okay, so that's why we are not going to use this exact analysis to analyze the circuit here, okay. So we are going to follow some approximate analysis, to analyze the circuit that is involving what, that is involving diodes, right? Okay, so what is that approximate analysis and all those things we are going to see now. Okay, so everything is clear here up till now? Is everything clear? Tell me here. Yes, good morning here, good morning. Okay, tell me, is everything clear here? Yes or no? Okay, okay. So we got the equation for this simple circuit. V in, here you are having resistor and diode, right? Okay, so we got this equation, V in is equal to ID into R plus eta Vt into ln of ID by I naught plus 1. Okay, so this is the equation we got if we do the exact analysis. Okay, so solving that equation is very difficult here, so we are going to follow approximate analysis here. So what is that approximate analysis? We are going to see that. So that is nothing but piecewise linear model here, So how we can develop this piecewise linear model and all those things we are going to see here. So piecewise linear model. So now here, see, if you observe the characteristic of the diode, so this is Vd, right, and this is nothing but Id. So we got the characteristic like this, yes or no? Right, okay. So we are having the characteristic like this. Okay, so this is exact characteristic of ID versus Vd. So now here, what do you mean by piecewise linear model means? So I have divided this characteristic here. Into different regions. Yes or no? So this is nothing but reverse bias region. Right. Okay. So this is nothing but the forward bias region with negligible current. Okay, so this is nothing but the operating region. That is in forward bias. It is operating in forward bias region. Yes or no? Okay. So this is what we have done here. Okay, so now see here. So now what I am doing here is, so I am taking all the different sections here. Okay, so I am each and every section I am representing with a straight line here. Yes or no? Okay, so I am taking each and every section and I am linearizing that section here. I am going to represent with some straight line, okay, in that section. Okay, so how we are going to do that? See here. Now this region here, this is non-operating region here. This is nothing but breakdown region, right? So this is nothing but breakdown region, that is non-operating region. Okay, so from here to here, you can operate the diode. In this region you can operate the diode. Yes or no? Okay, so now I am taking this section here, from here to here, from here to here, from here to here, the current is almost negligible. The current is almost negligible. It is almost equal to 0. So I am considering from here to here, the current is what? The current is almost negligible. That is equal to 0. That is equal to 0. Now here you are having the curve like this. Okay, so this is section here. This is section also I am linearizing here. That means I am representing simply with a straight line. So instead of representing it like a curve like this, okay, I am going to represent this with what? This with a straight line. This with a straight line like this. Okay, so finally what I am getting here is this is VD and this is ID. So here the current is approximately 0 is, okay, here the current is 0, and here this is cut-in voltage here. This is cut-in voltage V gamma. So from here I am linearizing this section also. Okay, so here you are going to get a straight line like this, right? Okay, so this is the approximate model. This is the approximate model, which we call it as what? Piecewise linear model, because piecewise we have taken different sections, and that means different pieces, and we have linearized that curve. Yes or no? Okay, so that's why it is called as what here? Piecewise linear model. Piecewise linear model. Now here, what is the slope here? What is the slope of this one? Slope is equal to what? Slope is equal to, the slope is nothing but the ratio of what? The ratio of change in ID by change in VD. So this is V gamma. Let us assume the diode is operating at VD. So let us say this is VD1 here. Let us say this is VD1, right? Okay. Okay, so the current that is flowing at this VD1, the current that is flowing here is ID1. Let us say this is ID1. So then what is the slope here? What is the slope of this curve? The change in VD by change in ID. Change in ID by change in VD. Yes or no? So what is change in ID here? Change in ID is nothing but ID1 minus 0 divided by what? Divided by change in VD is nothing but VD minus V gamma, right? Okay, so that is VD1 minus V gamma. So this is I by V ratio. That means I can write it as what? I can write it as 1 by resistance. I by V ratio will give you what here? Conductance. So I can represent this as what? 1 by resistance. So here this is the resistance. This is operating in which region here? This curve is present in which region? Forward bias region. And this is the resistance offered in forward bias region. So I am representing with what? 1 by RF. Right? Okay, so now here, from here, what I am going to get here? ID1, or otherwise I can write in this manner. See here. So if I reverse this one here, I can write this as VD1 minus V gamma by ID1 is equal to what? Is equal to RF. So therefore VD1 is equal to what here? Is equal to ID1 into RF plus what? Plus V gamma. Yes or no? Yes or no here? So that means the voltage drop across the diode, I can represent it as what here? I can represent it as ID1 into RF plus V gamma. Now if you observe this one here, if you observe this equation and this one here, that is whenever you are whenever you are doing the exact analysis, this is the equation we got. This is non-linear equation. Yes or no? This is non-linear equation. Here what we got? We got, whenever we have done piecewise linear model, we got what? We got linear equation. Yes or no? So dealing with linear equation is simple in dealing with non-linear equation. Yes or no? Instead of dealing with non-linear equation, we can deal with what? We can deal easily with linear equation. See, the advantage here is, if you do the exact analysis, or you can do this approximate analysis here. In both the cases, the results that we are getting are approximately same. Okay, the results that we are getting either by exact analysis or approximate analysis is almost nearly same here. So that's why we can follow, instead of following this exact analysis, we can follow what? We can follow this approximate analysis, that is piecewise linear model. So from this piecewise linear model, what it is saying is the voltage drop across the diode, is equal to what? Is equal to ID1 into RF plus V gamma, that is cut in voltage. So that means if you take the circuit here, let us say this is circuit, okay. So I am taking the previous circuit here, the same circuit, okay. So let us say this is VD1 here, and the current that is flowing here is ID1, okay. So now this VD1 is equal to what? Is equal to ID1 into RF plus V gamma. So that means wherever we are having this VD1, you can replace with what? We can replace with V gamma plus ID1 into RF. Yes or no? So how we can do that here? See here. So this is plus V in, and here it is nothing but what? It is nothing but R, and in place of diode, you can replace with what? You can replace with V gamma and RF. You can replace with V gamma and RF. Yes or no? Okay. So here, put here V gamma. Let us say this is V gamma, and here this is RF. Yes or no? The current that is flowing here is nothing but what? Is nothing but ID1. Now the voltage here, is nothing but what? The voltage drop here is nothing but what? Is nothing but VD1. Right. So the total diode here, I can replace with what? I can replace with V gamma and RF, that is a forward bias resistance. Now the current ID1 is flowing through this. So here this is V gamma, and here the drop is ID1 into RF, which is equal to what? Which is equal to VD1. That is equal to VD1. So I can replace this VD1, that is voltage drop across the diode, with what? With this equivalent model. So this is called as what here? Piecewise linear model. Right. Okay. So you can replace the diode with V gamma and RF. Okay. So that means, now what happens here? The circuit has become what? The circuit has become a linear circuit. Yes or no? The circuit has become linear circuit, and this is the equation that we are getting. From here, you can easily determine the diode current. You can easily determine this ID1 or not. Yes or no? So what is ID1 here? What is ID1? You are going to get ID1 is equal to what? Is equal to VD1 minus V gamma divided by what? Divided by RF. VD1 minus V gamma divided by RF. Yes or no? So you can simply determine the current in the circuit. Whereas if you do the exact analysis, it is going to be very difficult to determine the current. Yes or no? Okay. So we can represent this non-linear circuit in terms of what? In terms of linear circuit in this manner, by replacing the diode with what? By replacing the diode with its approximate model. Yes or no? That model is nothing but piecewise linear model. Okay. Okay. Yeah. Now see here, we can do further approximation here. We can do further approximation also. Okay. So what is that approximation here is? See here. Now here the slope is equal to what? Is equal to 1 by RF. The slope is equal to 1 by RF, and here this cut in voltage is V gamma. Okay. Now if I move this line here, if I move this line towards like this, okay, and if I make it straight line like this, okay, exactly here, if I move this line from here to here, exactly like this, okay. So then for this line, what will happen here? Slope will become what? Slope will become what? Slope is equal to infinity. That is equal to what? That is equal to 1 by RF. So 1 by RF is equal to infinity means RF is equal to what here? RF is equal to 0. RF is equal to 0. So what is the difference between this model and this model here? What is the difference between this model and this model? Here in this model here, in this approximate model, the slope is equal to what? 1 by RF. Yes or no? Whereas here the slope is infinity. That means you can replace RF with what here? You can replace RF with what? 0. Yes or no? Here you are having what? V gamma. Yes or no? V gamma is present as it is, but RF is becoming what? RF is becoming 0. So that means in this case here, you can replace the diode here. You can replace the diode with what? With V gamma. Simply V gamma. Yes or no? You can replace the diode with simply V gamma. Okay, why are here you are having RF, yes or no? So here RF is equal to what? RF is equal to 0, RF is equal to 0. So there is no need to represent this RF here. So RF will become 0, right? So in this model here, in this model is called as constant voltage model here, constant voltage model. So if you are having, so I am drawing here separately. So VD, ID, right? Okay, so this is nothing but V gamma, and for this one slope is equal to what? Slope is equal to infinity, that is equal to 1 by RF. So RF will go to 0 and V gamma, only V gamma is present and RF is will becoming equal to 0. So in this case you can replace the diode, you can replace the diode simply with what? Simply with cut-in voltage, simply with cut-in voltage. Okay, here RF is equal to 0. Okay, so this is another approximate model, or this is called as what here? This is called as constant voltage model here, constant voltage model. This is called as constant voltage model, right? Okay. Okay, next, if suppose if I move this curve here, if I move this line, okay, towards left and keep it exactly on ID, so then what you are going to get, tell me? So what is the change you are going to get, tell me? So here VD and here ID and here ID, right? Okay, now I have moved this line towards what? Towards ID and keep it exactly at ID. So then what will happen here? Okay, so exactly that means if I am moving this towards ID, towards this line, then this V gamma is decreasing, and if I move up to here, then V gamma will become what? V gamma is becoming 0, yes or no? Now for this curve, still slope is what? Still slope is infinity, that is 1 by RF, which is equal, this implies RF is equal to what? RF is equal to 0. Now this will become what? I have moved this V gamma from this location to this location, yes or no? Now here this V gamma is equal to what? Is equal to 0, Now in this case, how you can replace the diode here? You can replace the diode. Now here V gamma is also equal to 0 and RF is also equal to what? RF is also equal to 0. That means you can simply replace with what? You can simply replace with short circuit. Yes or no? So all these models here, all these are nothing but piecewise linear models, and this is having a specific name, that is constant voltage model, and this one we call it as ideal model here, So this is nothing but ideal model. Okay, this is ideal model, and this is what here? This is constant voltage model. Okay, and all these are nothing but piecewise linear models here. Okay, so we have analyzed how to represent the diode, with its equivalent model, whenever it is operating in what? Whenever it is operating in forward bias region, yes or no? So in all these three cases here, so whether you consider this one, okay, so whether you consider this one or this one, we have represented the equivalent model of diode in forward bias region. So now in reverse bias region here, so in this region here, in the reverse bias region, so you can replace the diode with what? Here the current is what? From here to here, throughout this region, the current is what? Current is negligible, yes or no? Current is almost equal to what? Current is equal to 0. The diode through the current is 0 here, and here also in this region the current through the diode is equal to what? Is equal to 0. And here also what we got here? Current through the diode is equal to what? Is equal to 0. So that means until it reaches V gamma here, until it reaches V gamma. That means if you are operating the diode below this cut-in voltage, then the current through the diode, is equal to what? Is almost equal to 0. So that means whenever you are operating the diode, such that VD1 is less than what? VD1 is less than V gamma. So if VD1 is less than V gamma, then current through the diode is negligible. Yes or no? Current through diode is negligible. That is approximately equal to what? Is equal to 0. In this case, you can replace the diode with what here? Diode is not allowing any current here. Yes or no? So you can replace it what? You can replace it with what? With open circuit. Yes or no? You can replace it with open circuit. So whenever the voltage drop across the diode is less than the cut-in voltage, there you can simply replace. You can simply replace the diode with what? Diode with open circuit. Yes or no? So this is the equivalent model of the diode here. This is the equivalent model of the diode. So what is the advantage of this equivalent model of the diode here? If you use this equivalent model of the diode, then the non-linear circuit will become what? Will become linear circuit, and it is very easy for us to analyze what? To analyze linear circuit. So whether we analyze through this approximate models, or if we analyze the circuit through the exact analysis, the results are almost matching here. The results are almost same. So that's why we always prefer these simple procedures to analyze the diode circuit. Right, we always follow this approximate model to analyze the diode circuits here. So whenever it is operating in forward bias region, you can follow either this model or this model or this model. Yes or no? Okay. So here in this model, you are going to have what? V gamma, some non-zero value, some cut-in voltage is present, and also you are going to have what? You are going to have some forward resistance. And here in this model, the forward resistance will become 0, and V gamma is going to have some non-zero cut-in voltage. And in this model, the cut-in voltage is equal to 0 and RF is also equal to 0. Okay, so here you can replace the diode with what? Simply short circuit. Here you can replace the diode with simply cut-in voltage. And here in this case, you have to replace the diode. In this case, you have to replace the diode. With what here? With cut-in voltage and resistance. So this resistance is RF and this cut-in voltage is V gamma. Okay. So finally I will give table here. So in forward bias region, so that is VD greater than V gamma, when VD is greater than V gamma. And in reverse bias region, or you can say simply when VD less than what? VD less than V gamma, where V gamma is nothing but cut-in voltage. So in this case, the diode can be equivalently represented with what? Can be represented with cut-in voltage and forward resistance RF and V gamma. Okay. Now here okay, next here diode can be replaced with what? Only cut-in voltage. Here RF is equal to 0. So you can draw the diagrams here. Okay, next for this one, so the cut-in voltage here is non-zero, and here slope is what? Slope is infinity, and RF will become what? RF is equal to 0. Okay, next Next one. Here slope equal to infinity and RF is equal to 0. V gamma cut in voltage is also equal to what? Cut in voltage is also equal to 0. Okay. Okay. So in this case you can replace the diode. You can replace the diode with simply short circuit. Short circuit. Okay. So this is called as ideal model here. This is called as ideal model. And this one is having a specific name. This one is called as what here? Constant voltage model. We can call it as constant voltage model. Okay. So in reverse bias here, that means when VD is less than V gamma, you can simply replace the diode. With what? With open circuit. In all the three cases, you can simply replace the diode with open circuit. Okay. Okay. So this is called constant voltage model. This is called ideal model, and all these models are called as piecewise linear models here. All these models are called as piecewise linear models. Okay. So this is how you have to replace the diode here whenever you are operating in a circuit. Okay. Okay. Yeah. So whenever you are operating the circuit, you have to replace the diode with its equivalent model in this manner. Okay. 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 So with this, I am winding up the session here. For today. Okay. So tomorrow I am going to start. We are going to deal with some circuits of diodes here. Okay. Okay. So today with this, I am winding up the session. Okay. So take care here. Bye bye.